In this module, we want to properly define now the acceleration. Before we talked about the average acceleration, and this is often called then the instantaneous acceleration, but really it's just the acceleration, and we want to establish the proper relationship between it and the velocity and the position. Previously, we learned that the velocity is the time derivative of the what I call trajectory, also often called the position, which is a function of time, which gives us the velocity as a function of time. And now, easily enough, the acceleration is the time derivative of the velocity. Now, of course, it would be a whole lot easier for me to simply write these as an equation to begin with, but that's not really the best way to remember it. The best way is to remember these relationships in words, and then we can represent them to any sort of equation that we want. So in sort of a vector equation, my velocity function of time is equal to the time derivative of the position as a function of time, and then our acceleration is the time derivative of the velocity. So if we're to look at just a couple of our examples from before, we had uniform motion in one dimension, and in one dimension we just looked at the components of the position. X of t is equal to x naught plus a constant velocity times time. And so our velocity function as a function of time was just a constant, v sub x, when we differentiated this term. And so our acceleration as a function of time is then the derivative of the velocity function, and the derivative of a constant is 0, and so our acceleration is 0, which is also consistent with our assumptions when we looked at velocity in uniform motion, or the acceleration for uniform motion in one dimension. Okay, well, that was pretty simple. We can look at a more complicated example. In the velocity module, we looked at a velocity that was of the form 15t squared I hat plus 2 minus 28 e to the minus 7t j hat. And from there, we could calculate an acceleration just like before. The acceleration then is the time derivative of these terms, and so the time derivative of the first term, let's sort of work through the derivatives. If you're new to derivatives, always some good practice. I hat for differentiate a polynomial, and now we differentiate this term. We differentiate each term separately. The derivative of 2, which is a constant, is 0, and so then the derivative of this second term, minus 28, the derivative of the exponential itself is itself, but then we have to differentiate, use the chain rule to differentiate the exponent, and that derivative is negative 7t to the 0, which is 1. It's just the j hat. And so our final acceleration is equal to 30t I hat minus 196 e to the minus 7t j hat. So this relationship gives us a nice mathematical relationship between acceleration, velocity, and position, and coming up with the velocity and the acceleration given an initial position is just an exercise in practicing your rules for differentiation. However, another nice way, which we talked about in the last module, to look at these relationships is through the position versus time graph. And so you can do that with the velocity and the acceleration as well. So we can look at position, velocity, and acceleration versus time graphically. Okay, so I'm going to use my favorite example, the one I had before. I have person with ball, throw ball up in the air, come back down and catch it. So what does this look like? Okay, the position versus time graph we had before. Again, it's not x versus y, but x versus t. It starts out at 0. To do that, I have to establish a coordinate system here. I'm going to have my 0 of my coordinate system where the ball leaves, and I'm going to have positive x direction going up. Really, every time you solve a problem, you pretty much have to have a picture that shows what's going on, as well as a schematic, a coordinate system with a 0 and a positive direction. Okay, given that, we can now plot the position versus time graph. The ball starts at 0, it goes up to some height, maximum height, and then comes back down to where it started. And it had, in the middle of this graph here is where it attained its maximum height. And so that's what the position versus time graph looks like. So what does the velocity versus time graph look like? So now I'm graphing the velocity, the x component of the velocity, as a function of time. And so before, we looked at that by looking at the slope of the tangent line of the position versus time graph, because the velocity is a derivative of the position. That gives us some information. So here, the velocity starts out large and positive, and it gets smaller and smaller until the point of maximum height, and the velocity goes to 0. This dotted line now is the same dotted line in time that is over here. This is the point where the ball reaches the maximum height. And now, you can't determine this qualitatively from this graph, but if you were to calculate it exactly, you would find that it goes from a positive value to 0 linearly. It's decreasing and decreasing linearly. Once it gets to the top, then it goes negative and it increases. And so the qualitative nature, that it starts out large, it decreases, goes to 0, then starts becoming negative and then more negative as time goes on until it hits the bottom, that you can determine qualitatively from this graph. Now, I've shown here that decrease is linear, and that you can't determine. You'd have to calculate that, but trust me at this point that's true if we're using this as an example. So once we have a velocity graph versus time that looks like this, we can plot an acceleration versus time. What does the acceleration versus time look like? So you see in this, while the position versus time was positive everywhere, the velocity versus time was positive for the first half and then negative for the second half. The acceleration versus time now is the slope of the tangent line of the velocity versus time curve. So if I look at this point, well, this is just a straight line. So the slope is the same everywhere. And so the acceleration is simply constant. And the slope of this line is negative. And so the acceleration versus time is simply a negative constant line. It is constant, meaning it's not changing, and it is negative. So the acceleration versus time curve looks like this. All right. So there's the position, velocity, and acceleration versus time for just throwing up, the simple idea of throwing up a ball. Let's do another example here, a slightly more complicated trajectory. Let's look at, I have this position versus time graph that looks like this. So it goes up and then comes around like this, and then straight line, straight line. So I want to look at several different parts of this curve. I'll call this point, this is A and B and C and D, E, F. And I want to consider at each of these points, A, B, C, D, E, F, what can I tell about the position, the velocity, and the acceleration at those points? What could this graph tell me? All right. Well, at point A, the position is positive. It's above the x-axis. The velocity is the slope of the tangent line at this point, which looks like this, and so that's positive as well. What's happening to the acceleration at this point? Well, before A, the velocity is steeper. After A, the slope is shallower. So as the particle passes through A, the slope of the tangent line is decreasing. So the velocity is decreasing, which means the acceleration then is negative. The acceleration is decreasing the velocity. So at point B, the position is still positive. And what's happening to the velocity? Well, the slope of the tangent line is 0 here. So the velocity is 0. And what's happening to the acceleration? Well, slightly before, the acceleration is positive, and slightly after B, the acceleration is negative. The velocity is negative. The slope is negative. So the acceleration is still negative at point B, because it is decreasing the velocity from slightly positive to 0 to negative. Now at C, the position is still positive. It's still above 0. The slope of the tangent line is negative and becoming more negative as it passes through C. So the acceleration is still negative. You can see that during this entire trajectory, this curved trajectory is curved, has a negative curvature that gives us a negative acceleration through that entire range. Now let's look at D. At D, now the position is negative, it's below 0. The velocity is also negative because the slope is negative. However, the slope is becoming less negative as it passes through D. The slope is steeper on this side of D than on this side of D. The slope is becoming shallower, which means it's become less negative So the acceleration is positive. So now if we finish up on the straight line, for E, you still have a negative position, positive velocity, but it's a straight line, so the velocity isn't changing. The acceleration is 0. And for a horizontal straight line, the position is back above the 0, so it's positive. The velocity now is 0 because the position is not changing, and the acceleration then is not changing either.